Hello, I'm Aaron. This is my cosmology assessment where I create a hypothetical universe. A little about me first. I'm a student in the CC program, earning a BS in astronomy and planetary science. Over the summer, I joined a research field trip through the GEO program called ASU Universe. And that's a picture of me on the left holding a moon rock and a Mars rock at the Busick Center for Meteorite Studies in the meteor vault. The photo on the right is a picture I took with my phone of the Milky Way, where I was at the 90-inch Bach telescope at Kitt Peak National Observatory, where our group did some research. All right, to start us off, for this project, we were to choose our density parameters, and each one had to be 20% different than of our benchmark model, and our universe had to be less than 80% similar to our own. So for normal matter, I chose 0.125, dark matter 1, and dark energy 0.45. We were also given parameters that we were told to keep, like Hubble constant, CMB temperature, and radiation density. So if you follow along with me here, on the top left, these bullet points were taken directly from the Planck CMB simulator for our hypothetical universe. So how does our universe differ? Well, our universe is 10.1 billion years old. It's a closed universe. The multipole moment, or the L value, is the scale of L equals 164, which translates to roughly 1.1 degrees of sky. If you look at the bottom left here, we got the power spectrum, which is quite different than our power spectrum, and we'll get into that. But I marked the fundamental peak there at L equals 164, or roughly 1.1 degrees of sky. In the top right, you'll see the CMB anisotropy map taken with the Planck telescope. And on the bottom right is the temperature map of our hypothetical universe, which shows the anisotropies of the CMB. And here's a better look at the temperature map shown on the previous slide. It shows the fluctuations of the hot and cold spots of the CMB, and the map scale area covers about 1 degree of the sky, or about twice the size of the full moon. The angular scale of our anisotropies are larger than the benchmark model by about 0.3 degrees. The acoustic oscillations on the power spectrum associated with compressions are hotter, and the rarefactions are colder in our matter-dominant universe. Because our densities of the omega values total more than 1, our hypothetical universe is a closed universe. This causes light to bend inwards, giving it a larger scale of fluctuation on the sky. And this is due to the stretching of the angular scales and why the hot spots appear hotter and the cold spots appear colder. So you may be asking, why is the universe closed? Well, that's because gravity is the dominant force, and it slows the expansion rate and causes space-time to curve in on itself. Kind of like the ant on the basketball, the angles of triangles would equal more than 180 degrees. Comparing the power spectrum. All right, so if you look on the right, we got the two power spectrums. On the top is the hypothetical universe that I've created, and the bottom right is the power spectrum of the benchmark model. So what you might notice is that the fundamental frequency has shifted to the left, and it also has a slightly higher amplitude. This is caused by deeper gravity wells in our matter-dominated universe, and this is the reason the hot spots are hotter and the cold spots are colder on our CMB temperature map. Theta is our angular scale in the sky. It's 180 degrees divided by our L value. And smaller L values give larger angular scales, and larger L values give smaller angular scales. This is because they are inversely proportional to each other. Also, if you notice on our hypothetical universe, um, the Sachs-Wolf region is not a plateau. It kind of dips in. So in a closed matter dominated universe, um, on the power spectrum, it exhibits a dip rather than a plateau as a result of the strong spatial curvature and high matter density that suppress large-scale temperature fluctuations. The oscillations in the real universe show well-defined second and third peaks, you can see down there at the bottom. Um, but in our hypothetical universe, the peaks are kind of compressed and they kind of blend together. So they're not as defined in our hypothetical universe. The baryon to photon ratio tells us how many baryons there are for every photon in the universe. This value is important because it controls how efficiently elements like hydrogen, helium, and lithium form during Big Bang nucleosynthesis. We can determine the abundance of these elements in the early universe and compare them to our benchmark model. So we have some given values here for energy density, average energy per photon, critical density, and photon number density. And our goal is to get to eta there down at the bottom. Uh, Eta is our baryon to photon ratio, which we find by calculating the photon number density and the baryon number density. So the baryon to photon ratio is 1.75 times 10 to the negative 9 in our hypothetical universe. And that means that there are nearly 2 baryons per billion photons. And for comparison, the benchmark model has approximately 6 baryons per 10 billion photons. And while these two numbers are similar, the hypothetical universe has slightly more baryonic matter. As in the benchmark universe, photon density dominates the early universe, and the increased baryon density boosts the amplitude of the compression peaks in the power spectrum that we saw earlier, and produces a greater abundance of elements during Big Bang nucleosynthesis. So the temperature of recombination. It's basically when in the early universe, electrons and atomic nuclei were able to combine to form neutral atoms, and when high energy photons couldn't ionize them, like knock the electrons away. And this was due to the expansion of the universe, causing it to cool because matter density lowered. So for this calculation, we'll need our baryon to photon ratio, Q, which is the ionization energy of hydrogen, and that's 13.6 eV, and the Boltzmann constant. When calculating the temperature of recombination, we assume that there are just as many high energy ionized photons as there are baryons, as we did in our modules. The recombination temperature for a hypothetical universe is 7,824 Kelvin, which is significantly higher than the 3,000 Kelvin of the benchmark model. So what does this mean? Since ionizing photons disappear sooner in the early universe, neutral atoms recombine earlier at a higher temperature. Because recombination happens earlier, sound waves have less time to travel, resulting in a smaller sound horizon. And the increased baryon density creates stronger gravitational wells, which limits how much the oscillations can occur. So for the redshift and scale factor of recombination, um, they describe how much the universe has expanded since neutral atoms first formed. The redshift shows how much the wavelength of light has stretched in that time. And while the scale factor shows what the size of the universe was at that time, with today's scale factor at A equals 1. On the top left, we got our values of temperature recombination and today's CMB temperature. But for this calculation, we were given the CMB And we find a redshift of 2,865 for a hypothetical universe. That's slightly higher than the benchmark value of 2,724, and the scale factor is 3.49 times 10 to the negative 4 compared to 3.67 times 10 to the negative 4 in the benchmark model. In our hypothetical universe, recombination occurs slightly earlier. Though the difference is small, hydrogen atoms form at a very specific temperature, and the higher matter density allows this process to take place sooner, but just by a little bit, not by much. Matter radiation equality is a time when energy densities of baryonic and dark matter are equal to radiation density. Before this time, radiation dominated the universe's expansion, and after this point of equality, matter will take over the expansion. The redshift tells us how much the universe had expanded by that time, and the scale factor gives us a sense of the universe's size. We equate the matter and radiation terms in the Friedmann equation, as shown here, determine the scale factor of matter-radiation equality. We find a scale factor of 8 times 10 to the negative 5 for the hypothetical universe, compared to 2.86 times 10 to the negative 4 in the benchmark model. The corresponding redshift is 12,499, whereas the benchmark value is 3,500. Because the hypothetical universe contains significantly more baryonic and dark matter, matter-radiation equality occurs much earlier. This corresponds to the higher redshift and smaller scale factor. Because matter radiation equality happens earlier, density fluctuations can grow faster, letting primordial stars and galaxies to form sooner in our hypothetical universe. These early events also set the size of the sound horizon, which determines the angular scale of fluctuations we see in the CMB power spectrum. Does dark energy become important in our hypothetical universe? Well, dark energy becomes dynamically significant when its density surpasses that of matter. Prior to this point, matter dominates the expansion, slowing it due to gravity. In the hypothetical universe, the matter density is extremely high, so dark energy would become important much later than in the real universe. It would only dominate the expansion once the influence of matter diminishes. From our calculation, the scale factor is 1.36, and the redshift is negative 0.26, compared to the benchmark values of 0.78 and 0.3 respectively. So what does this mean? This indicates that the universe would need to expand to approximately 1.33 times its current size, and the negative redshift supports this, as it implies this event will occur in the future. Does dark energy truly become important in our hypothetical universe? No. Matter and gravity dominate this closed universe, and dark energy never reaches a level where it significantly affects expansion. Because the universe is closed and matter dominates, it will eventually recollapse. This ensures that dark energy never has a chance to drive accelerated expansion. So this slide is a summary of data and calculations, and it summarizes the main results of our calculations. Compared to the benchmark model, our hypothetical universe has a higher matter density, which causes earlier recombination, a smaller sound horizon, and faster growth of density fluctuations. As a result, primordial stars and galaxies could form sooner, and overall, these differences show how changes in matter and dark energy affect the evolution of the universe. So our next topic is expansion history, and we were to choose a time. So I chose Z equals 100 when matter dominates the universe, and we'll look at its expansion history from there. I picked this time because it makes the calculations a little bit simpler to work with, and we'll cover redshift and scale factor, expansion rate and critical density, curvature and radius of curvature, and how the expansion is accelerating or decelerating. Redshift and scale factor at z equals 100. So our expansion rate today is 1, and the calculated scale factor we did was 9.9 times 10 to the negative 3. So using these values in the Friedmann equation, we find a Hubble parameter of 75,363 kilometers per second per megaparsec. This scale factor tells us the universe was very compact and only about 1% of its current size. With the high redshift, it shows the universe was still very young and expanding quickly, which we can see in the Hubble parameter. Physically, this tells us that at this time, the universe was very young, extremely compact, and expanding rapidly, conditions that set the stage for the density fluctuations and structure formation we discussed earlier. Critical density and curvature. We begin with the given values and first convert the Hubble parameter at AZ equals 100 to SI units so we can use them in our calculations. The resulting critical density is 1.06 times 10 to the negative 20 kilograms per meter cubed. The matter density is slightly higher than the critical density, and this indicates that the curvature of the universe is greater than 1. So our universe is closed with positive curvature. Space is finite and spherical as illustrated in the accompanying image. Because of this positive curvature, triangles in this universe have angles summing to more than 180 degrees, which also affects the apparent angular size of features in the CMB, shifting peaks to lower L values. And just like in our yellow dig assignment with the ant on the basketball, the triangles in a closed universe have angles that add up to more than 180 degrees. And this makes the CMB fluctuations appear larger on the sky and shifting the peaks to the left on our power spectrum to lower L values. So here we have our parameters with the current radius of 12.1 gigaparsecs at z equals 100 and a scale factor of 9.9 times 10 to the negative 3. So we calculate the radius of the hypothetical universe to be about 0.12 gigaparsecs. When we compare that to the benchmark model at this time, the Hubble radius is 0.004 gigaparsecs. This indicates that the hypothetical universe is approximately 30 times larger in scale. Consequently, during matter domination, this large radius contributed to a faster expansion rate of the universe during this epoch. So for the acceleration of the universe, we're going to use the Friedmann equation, and we're going to rearrange it with P equals 0, since pressure is negligible during the matter domination. The calculation incorporates our previously determined mass density, and we get a resulting acceleration of negative 3.299 times 10 to the negative 29 meters per second squared. What does that negative acceleration mean? Well, it indicates that the universe is decelerating, with gravity slowing the expansion due to matter domination. This deceleration also reflects the strong gravitational influence of matter consistent with our early findings about the universe's positive curvature and density. So what is the fate of our hypothetical universe? Well, the characteristics we had were that it was a closed universe, matter-dominated universe. It had strong gravitational effects, and the total density was greater than the critical density. In the accompanying figure there, the hypothetical universe's density parameters are marked with a green dot, and they correspond to a future with a big crunch. Now, what this implies is that gravity will eventually overcome expansion, causing the universe to collapse back into a singularity. So even though there is dark energy in our hypothetical universe, it never really dominates. So gravity eventually wins. And if future cosmologists were to be looking up at the cosmos They would observe galaxies blue shifting as they move towards them, leading them to the conclusion that the universe has a finite size, a finite age, and a contracting fate. These results tie together the effects of density, curvature, and expansion history and the ultimate fate of the universe. And just some light humor since we're so far into this. Cookie Monster crunching some cookies and Captain Crunch flying through what looks to be a galaxy. And so this is a artist's conception of what the Big Crunch scenario would look like. To the left side is the past, which represents when the Big Bang happened. And then the right side shows the universe's future collapse back into a singularity. Will the Big Crunch eventually have another Big Bang or a Big Bounce? Well, that is up for debate and another cosmology class. All right, now for a summary of the expansion history. So this table here summarizes the key results of our expansion history calculations. It includes the scale factor, redshift, Hubble parameter, critical density, matter density, radius of curvature, and acceleration at our chosen time. Um, these values collectively illustrate how matter domination, high density, and curvature influence the evolution and expansion of the hypothetical universe. So comparing our hypothetical universe with the data sets from scientific data we've collected, if you notice, I put the K values on there because they weren't on there. But I placed the yellow dot to the right of the data set, and that is our universe where it would fall. Well, sort of. This is actually the closest approximation possible, as my hypothetical universe lies outside the experimental constraints of this plot. So my universe's combination of matter, dark energy densities fall outside the observationally allowed region in the matter, dark energy plane. Therefore, the hypothetical universe is not consistent with current experimental data, and we cannot consider a viable model. These results highlight the importance of observational constraints in determining the properties and evolution of the universe. In conclusion, while our hypothetical universe allowed us to explore alternative cosmological scenarios, observational data confirms that the real universe has very specific density and expansion properties that govern its evolution. Thank you for sticking to the end, and thank you for watching. All right, bye.